Thank you very much for the introduction. In this talk I basically want to answer the four following questions. I want to give a short introduction in what is SAP HANA. Then I want to explain how you can use it. The next question is why are we dealing with graph at all, and which features do we offer. And at this point I have to say that I will demonstrate a version of our labs which includes features that are not in SAP products, and we reserve the right to not offer these features in future products. Okay, so what is SAP HANA? So how many people have worked with SAP HANA before? Quite a few. So SAP as company is a market leader for business software, and this business software has to process a lot of data, and hence these applications need a database, and SAP HANA is the enterprise solution for that. So it's basically a relational database system. It's an in-memory database. That means that all data is lays in main memory in a very compressed form, and you can use it on-premise or in the cloud. And we within SAP don't think that's just a database, because we think it's more a platform, because we offer so much different capabilities like advanced text search algorithms, or processing geospatial information, or we offer also machine learning algorithms. Okay, so how you can use it. Usually SAP HANA runs in large server landscapes, but with the recently announced HANA Express Edition, you can download it and develop on it. And it's a stripped version of SAP HANA which is limited up to 32 GB RAM. So basically it can be used for your project as backend. Okay, before we come to graphs, let's give a little introduction, because graph is not graph. There are many different graphs. Let's talk about simple graphs or directed versus undirected graphs. And basically there are two major frameworks for graphs. The first one is, or graph models. The first one is the resource RDF, the resource description framework. And this is introduced for knowledge representation and semantic web. It represents the data as triple with subject, predicate, and object. And these vertices and edges don't have any attributes. So you specify a vertex has age, and then as object you use a literal, and it's a standard. The second big graph model is the property graph model. In this model, each edge and each vertex can have attributes, arbitrary many attributes. The edges, there can be more or arbitrary many edges between two vertices, and these edges are directed. And for our use case, in our use cases we have complex types and their relationships. We think that's the natural way to represent the data. So we use the property graph model. Okay, to explain why we are dealing with graph, let's have a look in how graph problems are solved traditionally. And traditionally, the graph algorithms are run in the application layer. So an application fetches all the data from the database, which it needs to, and then it runs the algorithm. That means that sometimes you have to copy the whole graph out of the database into the application, and you have SQL as interface, which doesn't offer a nice graph abstraction. And each application who wants to run a graph algorithm has to implement it on in the application. And a more modern approach is to use a graph database, which offers a graph abstraction, and now the application can push down the algorithm to the graph database, and the graph database processes the information and only returns the result. But this has also disadvantages. So usually you have to replicate your data from the database into the graph database, and you cannot combine it with different features that are already in the usual database. So you don't know, or it's not clear in any case if you just want to replicate the graph data or the graph data with some attributes, because you also want to process additional attributes. Okay, let's have a deeper look into the interfaces and the requirements for graph databases. And we think there are two different kinds of queries. The first one is somehow pattern matching or traversal style, and they usually are very local in a graph. They access only a short piece of the graph. They are highly selective, and typically they are read and write transactions. So a typical example is loading and updating a Facebook page. And for this type of query, graph databases usually offer some declarative interfaces like Sparkle, Cypher, or PGQL. And the declarative interface offers the abstraction from the how to what data should be provided, and it gives an optimizer the chance to deal with low-level stuff like selectivity estimations and parallelization. The second type of query is the graph analysis. Usually these graph analyses are much more complex. They touch the whole graph, and they are usually read-only. And typical examples are PageRank or connected components. And for these type of algorithms, graph databases usually offer APIs or domain-specific languages that are specified for these type of queries, which means that they offer constructs compared to general purpose languages, that you have the complete expressiveness, but they also add building blocks, which makes it easy to write it in a graph way, what you want to have. And typical examples, therefore, are GreenMal or Prickle. Okay, let's come to our approach. Our approach is to add graph functionality into the relational database system, and we want to offer equivalent graph abstraction as interface like graph databases do it. So for the declarative interface, we want to use OpenCypher, and for the analytical graph queries, we offer GraphScript, which is a language we defined, and in some minutes I will talk a little bit more about it. And within the database, we can process the graph data in a native and so in an efficient way. The big advantage is that the graph engine is completely integrated into HANA, so we are completely transactional. We do not have to replicate the data, and we can process the data, the most current data. So you never work on outdated data. And while we are, due to the fact that we are in the same process, we can have direct access to the data, which are already in main memory, because in HANA all data are in main memory. And our features can be combined with all other features from the database, like geospatial processing. And as persistency, we still use the tables of the database, so we reuse the infrastructure. What you need to provide to get this graph abstraction is basically a set of attributes which need to be there. So we need a key for each vertex to identify the key. We need for each edge the source and the target vertex, and a key because we want to have more than one edge between two vertices. And so we can create a column table, vertices, and define this with a key and additional attributes like you want. And then we have the edge table, in which you provide the key column, source and target column, and the source and target column should reference to the key column of the vertex table to enforce that the graph is consistent. And if you have this schema, then you can create a graph workspace, which is a metadata object, and it works as a view and gives you this graph abstraction. So in the graph workspace schema, graph workspace statement, you say which edge table, which vertex table you are using, and which are the attributes of the corresponding tables. And then you have the graph workspace. And if you want to apply an algorithm on top of the, and use the graph in the graph workspace, you just have to say, I want to use this graph workspace. From database theory, usually it's not a good idea to denormalize your data because you have problems with updating data. And now we have, we know that vertices need to be in a table, and then usually there is a type. So it can be a type of person and can be type of post. And sometimes it's better to have persons in a table and posts in a different table to, and normalize data. For this case, if you want to stay in your normalized data scheme, then you can also define views instead of tables and create a graph workspace on top of the view, and everything works. Okay, I want to use a little demo. I want to show a little demo, and for the demo I have here data that represents a social network. For vertices we have posts, persons, and labels, and for edges we have created, so a person created a post or liked a post, and a person can follow another person, and we build a graph workspace on top of it. And this is the basic to run all the graph algorithms. So let's get a little bit deeper to what we offer, and let's talk a bit about the declarative interface. So for pattern matching, we started to implement a subset of OpenCipher. OpenCipher is a project from Neo Technology, which publishes a part of the Cypher syntax for free that different database developers can also implement it. And we started, basically we can match edges and vertices, and we can express arbitrary complex filters in it. We can project the result and sort the result. So in the first example, we are looking for two vertices which are connected by two edges, and the first edge is of type creates and the second edge is of type likes. That means that we are looking for persons that created a post and liked their post. In the second example, we have a path, and here we are looking for persons that follow the person with name Franziska Schwarz. The follow, the edges in the path need to be follows. So this is defined here in the all statement. And from this persons, we need to we have a look in what posts are created by these persons. Okay. So let's get to the little data. Probably you can't read it. I'm sorry for that. So I have here an HANA Express edition, and I now have uploaded the data. So in the social network scheme, I have two tables, which you can see. Here's the edge and here's the vertex table. Now I create a graph workspace on top of it. And to execute Cypher, we need you need to create a calculation scenario, which is an analytical view. It's a specific HANA extension on top of it, and we need it because we need to specify on which vertex we want to apply the Cypher statement. So we create this calculation scenario. And if we have created the calculation scenario, the Cypher stands here. The rest of the calculation scenario can be viewed as a template, just copy it. And when we select the calculation scenario, we get the result, which in this case are two vertices from Franziska Schwarz. So this was the first example where a person liked and created the same post. And again, for the path, we create the calculation scenario, and we can select it, and we get all the posts that persons that directly or indirectly followed another person wrote or created. Okay. The next features we offer are built-in algorithms, and we have 3 of it. The first one is a neighborhood search. Neighborhood search is basically a breadth-first search, which returns the vertices and the level in which the vertices are. As input parameter, you need to provide one vertex or a set of vertices. You have to specify if the direction of the which direction or which vertex you want to traverse. If you want to traverse outgoing or incoming edges, or direction any. If you want to ignore the direction, you need to specify if you want to which levels you want to get as result, and these levels are the usual breadth-first search levels. And you can additionally apply vertex and edge filters. As output, you get a table. Here with, in this example, when we start from Frankfurt, so this is basically a small graph with vertices of German cities, and think of it as a transportation network. So when we start from Frankfurt and want to go outgoing edges from 0 to 2, we reach Frankfurt as zeros as the first, so the second level, it's the start vertex, Stuttgart and Munich in the second level, and Berlin in the Berlin in the second level, and Munich and Stuttgart in the first level. Okay, the second algorithm is a single source shortest path. Basically, you have to provide a start vertex and a weight, which we want to use to calculate the shortest, to define the shortest. And the weight needs to be a column of the edge table, so it needs to be an attribute of the of edges in general. And you can also omit it, then we take 1 as weight for each edge. And again, for the output, you get all reachable vertices with the cost to traverse from the start vertex to the corresponding edge. Okay, a third algorithm, we offer strongly connected components. So within a strongly connected component, each vertex is reachable from each other vertex, and this algorithm don't need any parameter. And as output, you get all vertices with a component number, and all vertices with the same component number are in the same component. Okay, let's talk a little bit about GraphScript. GraphScript is a domain-specific language that is easily designed to solve graph problems. And I will here I talk a little bit about the vision, what we want this language to be. It should be a high-level language. You should be able to write your own complete graph algorithm in this language, but we will also want to offer building blocks that are graph-specific, and they deal with low-level concerns. These building blocks can be typical standard graph algorithms. Vertices, edges, graphs, and other objects like paths and trees should be types of this language, which makes it possible that you can return a graph type as result and apply a second algorithm to it. So for example, for shortest path, you can return a set of paths or one path, and then you can loop over the set of paths, and for each path you can apply a second algorithm. And it makes it possible to optimize in the background, because when we call a standard, when we call an algorithm and we call it with a tree, sometimes we can use a much more efficient algorithm than if we call the same algorithm with a general graph. The idea is to make custom logic combinable with standard graph algorithms. That you don't have to completely write the complete algorithm on your own, but use these building blocks and use a little bit of your own logic in between, and this should be so flexible that you can solve all your problems for your domain. In the background, or we use just-in-time compilation for that. There is the goal that you have to write only in a high-level language, and we compile it in a low-level language and use this one. And our goal is to be comparable fast as if you would write your graph algorithm directly in the low-level language. So we want to offer you an abstraction, but we don't. We want to offer an abstraction, but we want to lose performance. I answers after talk. Okay, so here are a few examples like how the syntax would be. So GraphScript is a procedure language, and here we create a procedure. For this example, I want to calculate the average out degree of my graph. In the first line, I bind my graph workspace to a graph variable. Then with the vertices construct, I take all vertices out of the graph and get it as a multi-set. So a container, and I can do the same thing with the edges, and then I can count my elements in these multi-sets and can divide the number of edges by the number of vertices and get the average out degree. A second example shows some basic constructs. So here I have three built-in functions. I slightly want to adapt an is-reachable algorithm here. In the first line, I again take my graph workspace. Then I fetch an edge out of it, with a specific key, which I provided as input parameter. And then I take the target vertex of this edge, and I fetch a second vertex with key I took a second input parameter, and now I call this reachable built-in algorithm on graph G from vertex V to vertex V2 and get the result. Okay, and the third example is should show that we offer general purpose programming language constructs like that you can loop with a for each over a container and use if-else blocks. So here in the example, we want to sum the year of birth for two vertices if they are persons, whatever reason there might be that you want to do that, but you can do it. So you can fetch the graph workspace, get two vertices, can put these two vertices into a set of vertices, can loop about over this set, and with if you can query if the type is person, and in this case that it is a person, you can sum the year of birth. Okay, again I will show you that these examples work. So here, this is my first procedure with the average out degree. I just create the procedure, and then I can call the procedure and get the out degree. And with this reachable, it's the same. So here I can also specify. Here I've specified the input parameter. So I took edge with key 111 and a vertex with key 8, and I had a look if the target vertex of this key is reachable, and that's the case. And also the last procedure delivers a result. So in this case I get 3,980, so both vertices are probably persons, because otherwise I wouldn't I didn't get so much a so big number. So Okay, these are basically the features we offer. So not all features are in the product, but many of them are. And you, as I said, you can download HANA Express Edition, play on your own with it. Here is the link where you can easily download it. So you have to log in into an account. You can download it. You get an image of a virtual machine, and then just put it into a virtual machine, and everything is installed in it. Okay, thank you very much. Yeah. We have time for questions.
So first quick question, do you contribute anything of your work to the open source community? And the second one, you use OpenCipher for pattern matching, but you use your GraphScript developed by you for the other stuff. Is there something equivalent to GraphScript in the open source world too?
So the first question is no. Nothing is for open source, but you can use it for free, but it's not open source. You can build your open source application on top of it. And the second one, there are other domain-specific languages, but I don't know if they are open source. So there are typical examples, but I can't tell you if they are open source. The ones I know are not.
Was there a reason to develop GraphScript instead of using Cypher expressions as part in the OLAP? Because otherwise you have to maintain two parsers and two...
No, the point I wanted to explain is that we think that there are two typical types of queries. One is the pattern matching style, and there you can use this declarative interface and optimize it. But if you want to really to solve any problem, really completely domain specific, and you want to have the complete expressiveness, you need to have a different type of language. Yeah. Okay. Your question?
So I have a question about the mapping between relational, land and graph land. You started with an example where you showed us two tables, one for the vertices and one for the edges. And I noticed that in the edges was just like the mapping, like from the two parts. But then you wrote some queries where you were looking at the type of edge. So how does it work? Is there...
Okay. So basically what an edge needs to have a key and a source in the target column. But usually you want to represent also, so we allow additional attributes.
Okay.
And type would be an additional attribute.
Okay, so edges have attributes, so we can add as many as we like.
Exactly.
I have another question. I'm not sure if I can...
Yeah, sure.
So in the vertices table, I noticed that it's basically just a table. That is like in the graph workspace, you map it. You say like, oh, this table is going to be my edges. So does this mean that all the nodes in my graph will be have just the same fixed set of attributes or properties, or is it possible to have like multiple tables for the vertices with different attributes?
Okay, you need to provide basically one table or one view, and any attribute you want to have for all of vertices. So the columns in this table or in this view are a union about the attributes of all vertices.
Right. So we don't have when a property is missing for a node, you will have a null value.
Exactly, yeah.
So you don't have the actual flexibility of a native node a native graph database where you can have like this node will have property name 1 and this will have like completely different set of properties.
So the property graph model is schema free from the model, but in the physical representation here in our case we need to have some constraints. Yeah.
Yes. But you could devise a model where you could have like multiple vertex tables and just have more elaborate syntax to do the mapping, and then you could still have this, but you didn't build that yet.
Yeah.
Yet?
When you have the view, can you actually write on the vertices as well, or is it read only then? When you use
So
when you use a view,
I don't know if I get
for vertices.
Yeah.
With multiple tables as sources,
Yeah.
can you still write on the vertices? Can you still write back, or
yet we support writing by SQL only. So
Okay.
you update your data with SQL, and then you update the corresponding table, and everything then will be fetched.
Is it just for testing or also for production deployment? Free version, I mean. Can a client use it directly, or does it need
you can
buy a license of some sort?
Okay.
I mean, this is for testing for us developers, or is it also for firms?
You can develop on it, but for more concrete information, please contact the license agreement. There is a license agreement. Read it. I don't have all the details in it here present that I can explain it to you. Okay.